Okay, so we're recording, and here's where we left off last time. We were talking about how to turn triple integrals into triple iterated integrals, right? So it's kind of like with double integrals, except there's 3 instead of 2. That's one of the big themes, is look for the analogies. Everything's different, but everything's analogous. Right? So what we talked about was, given a big solid chunk like this, right? Step 1 is to slice perpendicular to an axis, such as here I'm taking slices perpendicular to the x-axis, right? Identify the bounds, right? So first and last slices. The first and last slices, well, here's the first one, so there's my lower bound for x. Here's my last one, so there's my upper bound for x, right? And then fix a slice. So we're going to set x to be whatever value that is. We're going to focus all of our attention then just on that x slice. And then we move on to the next axis, the next variable, whichever way you want to say it, and go through the process again, and then move on to the next variable after that. And having gone through all the variables, we'll have a slicing done. So we talked about all those details last time. So here's what it looks like algebraically. So we talked last time about what it looks like geometrically. Algebraically, we've got x going from x1 to x2. So there's our x bounds. Our outer, you'll notice, our outside integral bounds. Okay, then, for a given value of x, focused again on just that x slice. Now we look for the range of values of y. I emphasize, though, looking at the range of values of y on the x slice, right? Not on the entire solid. We're not looking, I don't care how big y gets over here. Not as far as this value of x is concerned. We'll get to these points over here for appropriate other values of x. But we need to know how the y bounds depend on x, and so only for that x slice. Because these y bounds depend on which value of x you're looking at, 2 consequences. For one thing, for the purposes of this second integral, we get to treat x as being a constant. Because it is. The y integral happens over this cross-section for which x never changes. Right? And secondly, these bounds will depend on x. Yeah? Everybody good? Okay. And then we move on to the next integral. We're going to fix a value of y. Let's see here. So we're fixing a value of y now. In addition, here's my y slice of my x slice. I'll tell you what, just to simplify just to simplify the picture, let me do that. Here's our x slice. Here's our y slice of our x slice. And then the last iteration, the last time through the process, the z integrals, right? Z is going to have a first point. You might say that this is the first z slice of our y slice of our x slice, right? Anyway, first value of z is going to give us the lower bound for our z integral, and then the last point up here, this last value of z, is going to give us our upper bound. Now again, notice on this y slice of our x slice, right? Not only does x not change, but also y doesn't change either. We're going straight up, right? So both x and y are fixed. So let's see here. Let me get this all in here. So for this inside integral, not only is x constant, but also y is constant. Both x and y are constant, and correspondingly then, these bounds, not only do they depend on x, they also depend on y. Okay, how are we doing? Everybody see how that manifests? I mean, so there's the picture that we talked about that's going to allow us to effectively slice up the entire solid. And then this algebraically is what it looks like and what variables are playing what role at what part of the calculation in the iterated integral. Yeah?
For the z, x, y, it's not the y of x, right? Or it's just...
No, that's right. Z2 is a function of the independent variables x and y.
Okay, so not like y of x.
Correct,
okay.
Correct. Y is not a function of x in here. The y bounds are functions of x over here. Over here, x and y are independent. Yep, good question. Anybody else? Okay. All right. So a little bit of terminology. Oh, and I should emphasize, I'm just trying to be consistent with my coloring here. Looking at the x slice there, but specifically we're looking here at the y slice of our x slice. Okay, so this is our whole picture, color-coded and everything. Keep in mind which variables are constants at what stages. There's an easy little memory tool for that, and that is whichever interval you're looking at. Whichever interval. The variables further to the outside are constants. Right? So for the inside integral, this dz integral, x and y, being as they are further to the outside, constant. Right? Likewise, for the dy integral, x is constant because, again, x is further to the outside. So that's a nice little memory tool. It's always a good idea to eyeball your work. Right? When you write down an iterated integral representing something, double check it real quick. Make sure that you don't have any bounds that are functions of anything other than variables further to the outside. If you do, what you've written down doesn't make any sense. It's not that it's wrong, it's that it's meaningless. Does that make sense? Okay. All right. So, a couple of quick observations, and then we're going to dive in to a bunch of examples here. So we construct the iterated integral outside to inside. So notice this process of creating this. We started with the outside integral and moved inward. Right? Outside, in. That's how the slicing process works. Now, of course, when you evaluate, just like with double integrals, you have to evaluate inside to out. Right? Okay. We've already talked about this next point. Each bound can be a function of variables further to the outside. Talked about that one already. And then I'm gonna show this kind of by examples. This is the same connect the dots of ideas that we talked about with double integrals. If you want to know what a bound is for one of your integrals, you need to identify what's the corresponding point. Which is on what surface or surfaces or curves or what have you. And what are the equations of those surfaces or curves or what have you. And then solving in those equations will give you the bounds that you want. So let's see that in action. Here we go. We're going to start off. This is kind of an easy starter example. It's a tetrahedron. That shape right there, you'll notice that that's the shape that's bounded by these four planes. A little bit of an artistic challenge to think about how these planes intersect and what's the resulting picture. This is the result. Make sure that you feel comfortable with that. Right? Take a little time to think about these planes and how they intersect, and make sure that you can come up with for yourself this picture as a result of this algebraic statement. Okay, so how to slice it. Arbitrarily, no particular reason, I'm going to do this order for my differentials. Doesn't really matter. In fact, in this case, it really very much doesn't matter. There's a lot of symmetries here, and any ordering of the slicing that you do here is pretty much going to work out. I pulled this one out of a hat. Okay. All right, so starting with x. What's my x bounds? Well, there's the x-axis. These are what x slices look like, right? Perpendicular to the x-axis. Remember, a slice perpendicular to an axis represents a constant value of that variable, so perpendicular to the axis. And then where's the first and last? Well, here's the first one. And here's the last one. Right? Those are the first and last of our x slices. Everybody okay? It's all geometric appeal so far. Let's think about the bounds. We'll start with the lower bound. This is kind of an easy one. Lower bound for x. I can see the entire slice, and in fact that entire slice is in the YZ plane, otherwise known as x equals 0. So if you want to know what value is x, when you're in the plane x equals 0, well, it's 0. Right? Freebie. Read it straight off of the picture. Really not, there's not any algebra required there. It's just self-evident from the picture. But let me make sure everyone's okay with that. Is everyone comfortable with my assertion that this is where x equals 0? Okay. All right, last slice. This one's a little more challenging. The last slice is that point right there. We're going to find our upper bound for x by looking at this point. And recall, bounds that you identify based on certain points. We've identified the point. I need to figure out what surface or surfaces is it on, and I need to write down their corresponding equations. So let's do that. This is where the picture is indispensable. You really got to have the picture for this. That point, I can just see from the picture it's on that plane among a couple of others, but it is on that plane, which has that equation. Anybody see that from the picture? Okay. Here's the other thing, though. It's also on this plane. Again, I can see that from the picture. I see where the point in question is from the picture. I see what planes it's on from the picture. That plane has that equation. And then lastly, I also see that this point is also on that plane, which has that equation. Right? So this point that I'm looking for, this point whose x-coordinate I need to understand, is on the intersection of all three of these planes. Now, keep in mind, it's easy to lose track of what we've been looking at this point and thinking about planes and writing down equations, but why? What was I doing? What do I want from this point anyway? I want to know x, right? I'm looking for x bounds. So in this trio of equations, I need to solve for x. Not much trouble to do so. You get 1. So our upper bound for x is 1. Everybody see the process? Okay. Now, I want to recognize that, you probably kind of just from the algebra, probably without even really thinking about it too. You might have noticed already that x was equal to 1 at this point before we even started this process. It's a very simple little tetrahedron. The point to this is not that the answer is 1. The point is the process. That I identified the point, I identified corresponding planes, which have certain equations, and then I solve for the variable whose bound I'm interested in. Yeah?
Can you explain how you drew the graph?
How I drew this picture?
Yeah.
So that's, let's see here, how to justify this. I got 3 coordinate planes. Right, and so that's that and that and that. And then I've got this plane x plus y plus z equals 1. And, flashback to chapter 1, I can see what the normal vector is here, right? The normal vector is 1, 1, 1. And I can also notice a couple of freebie points that this includes, perhaps, right? And I just have to use those chapter 1 methods to sort of visually see that this is a plane sort of oriented about like this. And now just ask yourself, how does that plane cut through these other planes? Right? It's kind of a geometric challenge, and that ends up being, of course, that. And once you see all that, then you have to peer inside and notice that this solid tetrahedron is what's bounded by those planes. Is that okay? Is that satisfying? Okay. Cool. All right. Okay, next bounds. Let's, as per the instructions, we're going to fix a value of x. So we're now focused only on this x slice, arbitrary x slice. Moving on now to the next variable, y. And I got to ask the question, I got to think geometrically, what happens when I take slices perpendicular to the y-axis? Well, perpendicular to the y-axis, it's kind of like that. And you got to think through geometrically. I've got this slice, this x slice, and then I'm slicing y slices of that x slice, and I just appeal that you get these little segments that look kind of like that, right? So my various y slices look kind of like that. Everybody okay? All right. Oops. Okay. All right. First and last. Here's the first y slice. Again, just looking at the picture, looking at all the different y slices. That's the one with the lowest value of y. Here's the thing, it's in the XZ plane. You see it right there in the picture. I don't need to enumerate a bunch of other stuff about that slice. It's clearly in y equals 0, so therefore y is 0. So again, sometimes you get lucky, things work out easily. For the upper bound, again, a little bit more work has to be done. For the upper bound, there's my last y slice, right? To find my upper bound for y, there's my last y slice. Now I got to look at that point. I got to go through the analogous process. What do I know about this point? And then, again, solve for what I want. So here we go. First thing I can say about that point, and that is, I know what x is. Now, this is a silly way to write that down, and I apologize for that, but writing x equals x, that's kind of that's the way in my mind is. I find that's a satisfying reminder that x is fixed. I'm allowed for my answer to be in terms of x. I don't need to solve for x. I can leave my answer in terms of x. So I write that down. What else do I know about this point? Now, again, the picture tells all. You've got to have a good picture. Very, very important. So what else can I say about this? Well, there's this plane, right? The point in question is in that purple plane that has that equation. And I can also see from the picture, the blue point in question is also in that plane, which has that equation. So that identifies, that defines this point. There's exactly one point that's in green, orange, and purple together. That's the point I'm looking for. And so in this algebra, I need to, by the way, again, I forget what I'm doing. What am I solving for? I'm solving, it seems, for y. Right? So in all of this algebra, I'm going to solve for y. And when you do that, you get 1 minus x. Notice, allowed to be a function of x because x is further to the outside. Here, let me do this. X is further to the outside, so I'm allowed to have that be a function of x. And that's what goes there. How are we doing? Everybody see the process? Again, the specific answers here is not the point. The point is, does everybody see the process and how I'm approaching this? Okay. Alrighty. Last one. Okay, let's see here. We've fixed a value of x. We fixed then a value of y. In other words, we're going to look at this y slice of this x slice. So, x is known. I don't need to solve for it. I can leave my answer in terms of x. Y is known. I don't need to solve for it. I can leave my answer in terms of y also. And we now want to look at z. I want to know starting and ending values of z. Z starts there, which is clearly in the plane z equals 0, and so z starts at 0. Again, sometimes it's easy, sometimes it's just right there. Where does z end? Z ends at that point. And what do I know about that point? Well, again, I already know x, I already know y. Those are given. And the last thing I know is that it's on this plane that has that equation. Again, we're solving then for z in all of this algebra here. You solve for that z. Your answer is allowed to be in terms of both x and y. because x and y are constants. X and y are further to the outside, so that's okay. And our upper bound for z is there. What do you say? Yes?
Oh, I was just kind of wondering, like, we've been looking at, like, the ends being, like, points, but, like, what if it was, like, chopped so that, like, the last y was, like, a line?
Yeah, well, all of those, that's a great question. All of those will have the same value of the coordinate that we're interested in, because if it's on the same slice, then that, keep in mind a slice represents a constant value of that variable. So then you can kind of pick whatever point you want on that slice. Yeah, you have options there. So that's a good news, not bad news kind of a thing. Yeah. Yeah, great question. Anybody else? Okay. All right. Okay, a lot of junk to erase there. Okay, so, heads up. You do have 6 different orders to choose from here. That's a good news, bad news thing as well. The good news is you got 6 different options. That's a lot of options. You got a lot of flexibility. I guess that's a good thing. The bad news? You got 6 different options, and you have to distinguish between the 6 different options. So it's a double-edged sword. It's a lot of things to think about, but it is good to have those options. Okay, so you want to make good, thoughtful choices as to which way you slice. We're going to recover a couple of rules from double integrals that apply equally for triple integrals. Try not to slice through corners for pretty analogous reasons. If you slice through a corner, then for the next inside integral, your bounds are going to be all messed up. You're going to have to break it up into 2 pieces. It's a headache. All else being equal, if you can avoid it, best to avoid that. Okay. Similarly, keep in mind, whatever is the variable on the inside, z in this case, whichever variable is on the inside is the one that you're going to have to solve for in terms of the others. So be thoughtful about which one would you rather solve for. If one of the variables kind of is naturally, in the algebra you've been given, naturally a function of the others, and you really don't want to have to turn it around and solve for the other variables, put it on the inside. Right? And then you won't have to solve for the other variables. You'll have to solve for the one that you've already solved for. And that's a good thing. Okay, so all of that is just like with double integrals. There is a third tool that I'm going to give you here. I think this is really good. I wish the book spent more time talking about this. I use this a lot myself when I'm doing triple iterated integrals. And that is this is the idea of a good projection. And there's various things to say about what makes a good projection. And I've got them kind of bullet pointed here. The thing is, it makes a lot more sense to see it in action, in example. So what we're going to do, I'm going to start off doing this example, and then I'm going to go back up to what I just skipped and point out how what we're going to see here is an example of what I'm talking about with a good projection. Okay, so here we go. First octant, z equals 1. Z equals x squared plus y squared. And if you think about how those surfaces intersect, your solid looks kind of like this. Something like that. All right? Everybody good with that? Flashbacks to chapter probably 2, I guess. Chapter 2, when we thought about how to plot these kind of surfaces. Anyway, this is what we get. Okay, so I look at this algebra. I see that surface is part of the boundary of my domain. And when I'm doing my slicing, I would really love it if I need to solve for z, not x. Right? All else being equal, I'd prefer not to have to solve in this equation for x as a function of y and z. Not that I can't do it, but I just don't like square roots. Right? So I think it's a pretty natural choice because z is a function of x and y, let's choose to put the z on the inside. Everybody see my motivation there? This is just using this trick right here. Whichever one's a function of the others, I mean, if the option's available, if you can, put put that one on the inside, like I did here. Okay. So, yeah, arbitrarily I'm going to do the other variables in this order. You're going to see momentarily that it kind of doesn't matter which order you put these other two variables in this case. Well, let me give you 2 points of view, though, on how to think about doing the slicing process with this choice made for how I'm going to order my differentials. And notice the first thing I have to do is my y slicing. So there's the y-axis. Here's what y slices look like. Right, that's a constant value of y. Slicing up this solid, I get a picture that looks kind of like that. There's my y slice, a y slice. And, you might not be able to tell, but that's a hard picture to draw. It's really pretty challenging. If you don't believe me, take out a clean sheet of paper and draw that yourself. Right? It's tricky. By the way, I'll also pitch. Y'all heard me say this before. I'm sure I'll say it again. On my YouTube channel, I have these various recordings of things that I think students very often kind of need some extra help on, and one of them is how to draw three-dimensional figures. So if you go to my YouTube channel, Miscellaneous Topics playlist, there is a pair of recordings called Drawing 1 and Drawing 2, in which I explain in great detail how to draw this exact figure and how to draw it well. And I'm going to say I think I did a respectable job there, but it took me a while. That was probably 45 minutes, right? Because I wanted it to look really nice, really presentable. But it is a tricky bit, right? And if you want to see the explanation, I encourage you to take a look at those recordings. Okay. All right, so there's my y slice, and I can talk about where it starts and ends, and then I can talk about x slices of my y slice. Here's what x slices look like. They're going to cut through there kind of like this. Right, after which I can then talk about z going from sort of there up to there. And there's nothing wrong with making this argument. The only problem with this is it's just hard to draw. You got to have a pretty respectable three-dimensional figure in order to be able to think comfortably about what the cross-sections look like and the starts and ends are at which points, which are on which surfaces. Your figure needs to be reasonably representative. Okay. All right. So here's the alternative. The projection alternative. I claim that we're going to have a good projection into the XY plane. Now let me draw that first. Let's see here, I'll use green. Okay, so by projection to the XY plane, of course, I mean just look at the shadow, push everything straight down. Here's my projection into the XY plane. And I claim this is a good projection per the following criteria. The shadow is nice. There's nothing particularly wrong with this shadow. Okay, sure, it's got a curved edge over here. What are you going to do? There's clearly curves. Whichever way you project it, you're going to have a curve. Not that bad. So it's kind of okay. All right. Next, I claim that we've got a nice top surface. The top surface, I claim, is consistent and desirable. Let me show you on the picture what I mean by that. By the top surface, what I mean is that if you pick a point down here in the shadow, and if you look at the range of values of the inside variable, dz, right? Look at the range of values of the inside variable for that point. That end point, the last value of z, the last value of the inside variable, always on that surface right there, which has a really easy equation. So I'm going to call that highly desirable. This as a top surface, that equation is wonderful. And furthermore, it's consistent. What I mean by consistent is it doesn't really matter where this purple point is. Wherever you might happen to be in this projection, that top point always on the same surface. It's not like sometimes it's on the one surface, but then there's a an edge, and then for other points it's on a different surface. No, it's always this same surface. Okay, so consistent and desirable. Likewise, the bottom surface. Also, I claim consistent and desirable, and we can see that down here. The bottom surface, you notice this first point for Z. Always on that surface. And, not as desirable as this equation, right? But no square roots. Nothing all that bad. Okay, sure, fine. It's not a constant. It's got a quadratic in it, but in the big scheme of things, it's pretty good, right? So always the same surface, consistent, nice equation, desirable. So this is what I mean by a good projection. Good projection into the XY plane. Good shadow, top and bottom surfaces, consistent and desirable. The reason I like this, the reason I call this a good projection, is because I claim in this situation, the projection gives you the bounds for the x and y integrals. So we've projected down here to the xy plane. Let's think about what the bounds are. I'm going to erase all this now. Let's see here. Let's talk about what the starting and ending values of y are. Y goes that way. There's my first y slice. There's a representative y slice. There's my last y slice. Here's the thing. On the projection, there's the first y slice. There's the representative y slice. There's the last y slice. And notice they're straight up and down from each other. No surprise. What we have down here, of course, is literally the shadow. It's what you get when you push straight down. When you push straight down, you're not changing y coordinates at all. So the range of values of y on this complicated picture that's hard to draw, that you don't want to have to draw, well, that range of values is the same as the range of values on the much easier to draw shadow. So just draw the shadow. You don't have to draw the whole thing. Everybody with me? Okay. All right. Likewise, and let's see, I guess I'm going to zoom back in. Looking at a y slice, here it is. Here's the projection also of our y slice. Let's think about now the range of values of x. Well, on the actual slice, first, representative, last. On its shadow, first, representative, last. And again, notice straight up and down, right? There's nothing that really happened there as far as x is concerned. All of these x coordinates, first, representative, last, exact same as if I were looking at this very hard to draw actual slice of an actual solid. So you don't have to draw a solid exactly. I mean, you do need to draw it well enough to understand what the projection looks like, establish that it's a good projection. But this is where you actually are going to focus your attention. And then, of course, notice that this projection, let's see here, back to green, this projection, that's just quarter disk. Quarter disk is really easy to understand. Here's a little algebra to kind of make sense out of it. But the quarter disk, easy to break down its bounds. The xy bounds, then, are just that. It's basically a double integral question. Everybody see what happened there? It's a really neat trick. It saves us a ton of trouble. And even more so in another couple of cases that I'm going to show you coming up here in a second. So this is a sometimes tool, as are all tools in our toolbox. Keep in mind that that tool is in there. Use it when it seems like it might be convenient and useful. You don't have to use it, and there's some situations where it's more trouble than it's worth, right? But in a case like this, I think it's very nice to think about the x and y bounds. Now, again, I emphasize, this only works when you're talking about the two variables furthest to the outside. Your outside two variables. You can look at the projection, find the bounds on the projection. Very handy. Did I see a hand somewhere? Yeah.
I'm just kind of trying to imagine like a scenario where that like wouldn't work. Like,
Oh yeah, no, you can't. It always yeah.
like,
Oh, you're wondering. Oh, when it wouldn't be when it wouldn't be a good projection.
Yeah.
I'm going to show you one. I've got it's a couple pages forward.
Okay.
Yeah, so bear with me. Yeah. Okay. Alrighty. Let's see another example. This next one is even harder to draw, honestly. Oh, I'm sorry. You had a question.
I was just going to ask, why did we have to put the bounds, the lower bound for z as x squared plus 4?
You know what? I totally spaced and forgot to finish the example. So yeah, thank you for reminding me. Okay, let me get exactly to that. Then here's our projection. That's our xy projection. These are our xy bounds. And what I did forget to do, I guess I'd better zoom out, is point out then that for a given value of x and y, right? In other words, looking at this, let's see, x slice of my y slice, right? We've got to look at the starting point for z. That starting point for z, though, by design, is always on this one surface that has a desirable equation. And so solving for z, because we're looking for z bounds, that's what you get when you solve for z. Does that make sense?
Yeah. So if you just had 0, it would be the volume of the quarter cylinder.
That's right. If the solid had gone kind of all the way down to here, yeah, that's right, it'd be kind of a quarter cylinder. That's right. Yep. But it's not. So it's the lower surface is this paraboloid, indicated by this being the lowest point, and so thus this. Yeah. And then the upper bound, just for the sake of completeness, right? The last point, again, by design, we arranged. We only did this because we noticed that this surface was always going to be our upper surface, and solving for z on that, we get z equals 1. Okay. All right, let me show you another example. Again, I claim this one's even harder. Even harder to draw. It doesn't look harder to draw, it's just a ball. A lot of people would say, yeah, it's really easy to draw a ball. It's just round. You just do like that. Boom, ball. Right? The problem is, I'm going to need to draw a slice of that ball, and then I'm going to have to visualize slices of that slice, and it starts to get surprisingly uncooperative. In other words, you'll think you're fine, you draw your slice, then you draw your slice of your slice, and you realize, no, my picture's terrible. It's surprisingly challenging to do a good job with this. This was another very hard figure for me to draw. So, you can do it that way. Slice your slice, etc. But it's so much easier with a projection. So, for no particular reason, again, we have a lot of symmetries here. You really can do it in whatever order you want. But I'm going to do z and x on the outside. With z and x on the outside, I can think about my bounds in terms of how they project into the xz plane. And it may be a little bit hard to draw, but it's not hard to understand that the xz projection of a ball is just a disk. Right? And this is a unit ball, and so this is just a disk of radius 1. And the x and z bounds, when you're talking about a disk of radius 1, it's a double integral slicing problem. You just draw a disk of radius 1. X goes from -1 to 1. Z, solve for what z does for a given value of x, and boom. And again, we're 2/3 done. And we haven't had to do any ugly slicing. This is a very powerful triple iterated integral trick. How we doing? Is everybody happy? Okay, and then, then there's the little details of, okay, well then, yeah, but for a given value of x and z, wherever I might happen to be looking, I've got to figure out where does y then start and end, right? Y, well, it's going to start at that point. It's going to end at that point, both of which are on the sphere. Solve for y on the equation for the sphere, and you get those inside bounds. there. So again, artistically very convenient, very streamlined, using the projection trick. Okay. Excuse me. Okay, now somebody asked me, what does a bad projection look like? This is a great example of a bad projection. I'm going to have to work up to it. The question as stated is this. You'll notice we have 5 planes. And we're looking for a solid that's bounded by these 5 planes. And you know what? Generally speaking, if I were to give you 5 random planes and ask how do they intersect, some of them will intersect, some of them won't. Some of them will intersect kind of outside of the region that we're interested in, and therefore their intersections don't matter. It's a horrible headache, nightmare of a question to figure out how 5 arbitrary planes intersect. Very, very tough. That's not what this is. There's a very convenient trick here. I hope you'll be very much on the lookout when you see this kind of thing come up, not just on homeworks and my exams, right, but also outside of this class. And there's a little bit of a flashback to chapter 1 here. 3 of these equations don't have any y's in them at all. Y'all remember that from chapter 1, right? When you have a plane that doesn't have any y's in the equation. Different ways you can think about it. You can think about which way is the normal vector point, etc. But these are therefore parallel to the y-axis. So flip back in the notes if necessary. This is in chapter 1, fairly early in chapter 1 as I recall. Nice fact to have to take advantage of. So the reason this is helpful is because that means it's easy for me to draw these 3 planes. They're parallel to the y-axis, so if I know what they look like for any value of y, so here I've drawn what these 3 planes look like in the y equals 0 plane. Well, the actual planes themselves are just what you get when you drag that parallel to the y-axis, because the planes themselves are parallel to the y-axis. So seeing what they look like here, I can tell that I'm really going to be looking at this triangle. That's going to be dragged kind of like that, parallel to the y-axis. I've got basically a prism, right? And so I'm 60% of the way there, 3/5 of the way there, just from this one observation. So also very cool, very convenient. What do you think? Not done yet, of course. Okay, so what about these other planes? What do I do with y equals 0? I mean, how does that factor in? It does have a y in it, right? So it's not parallel to the y-axis. I can't use this particular trick. The good news is, though, again, with having a picture kind of started, I've got my foot in the door, and now I can just literally just kind of brute force it. I can think about, well, how does y equals 0 intersect with this prism? And not so bad to think through. Again, it's, 3-dimensional thinking. You do have to kind of, draw it and or see it to persuade yourself that this is what happens, but it intersects kind of like this. And then the hard one, it's just kind of no way around this. The last plane here, this purple one, it's not parallel to anything, right? But it's also not that bad. It is I know where it intersects the coordinate axes because I can just see x equals 3, y equals 3, z equals 3. So I know it intersects kind of there and there and there, and so I can kind of draw that. And now I just think geometrically, if I have a prism out here like this, right, and if it gets cut at kind of an angle like that, then it's going to kind of leave a slice sort of kind of maybe like this here. What do you think? And thus, final picture, this final picture right here. If you'd like, if you're having a little trouble perhaps seeing how this final cut happens, one thing you can do is solve for this point. right? You can see which 3 planes it's on to find exactly where that is. That'll help you draw where that corner is and therefore kind of get these edges kind of angled in the right direction. And likewise, you can solve for where that point is. And that'll, make your picture maybe a little bit better. But roughly speaking, that's what we've got. Okay, now I claim this is an example where we have bad projections. There's actually a bunch of bad projections. There is a bad projection, I claim, down to the XY plane. Now the shadow looks fine. Nothing wrong with that as a shadow. But let's talk about what is the upper surface. In other words, if I move up from there, right, where's the last value of z? And what you notice is that where that last value of z is kind of depends on where you are in the yellow projection. Sometimes that last value of z is on that surface. But sometimes it's on this surface. And so that we don't have the consistency that we need. So this is a bad projection. And I strongly encourage you not to try to make a projection argument from this point of view. It's just, it doesn't work. Does everybody see the problem? Okay. All right. There is, however, a good projection, in this case, to the XZ plane. Again, coincidentally, same as before. But the projection to the XZ plane, not only is that shadow nice, but furthermore, the lower bound surface is always that same plane. The upper bound surface, always that plane. So we have a nice consistent upper, nice consistent lower, and a nice shadow. That's a good projection. And it's that's the way that I encourage you to make these bounds. To think about the projection, your X and Z bounds come from the shadow. Right, looking at that shadow gives you your X and Z bounds. And then you just have to think about, alrighty, well, the lower bound for Y is on that surface where Y is equal to 0. And the upper bound for Y, that upper bound point is on this surface where, you got to then solve for Y in this equation. In this way up here, in this equation way up there, right? But solving for Y, easy to do, and you get your upper bound is that. Okay. Everybody on board? If you're looking for a little bit of an exercise, this is a mathematical weightlifting, as I like to call it. Something that doesn't really accomplish anything, but will make you stronger. Right? Think about how you would slice if you were to not use the projection trick. If you were to think about different ways that you can slice. There's 6 different ways that you can slice it. Right? And think about what those options are and which ones are good and which ones are bad. I think what you'll find is that doing your Y slicing on the outside is bad because you're going to slice through this corner. That's not good. And then in fact further over, after that, you will slice, you will slice through this corner. And everything's just all messed up. So putting dy on the outside would be a catastrophe. Likewise, I claim putting dx on the outside, catastrophe. And again, of your 6 options, there's only one that works. The only one that works is the one that we used over here from the projection point of view anyway. So again, good little exercise. Think through the other 5 different options and see why they're all bad. You always hit a corner, basically. Okay, last example. I think this is the last one. Yeah. Real quick, it's just another example of the same thing. Here I have a surface there. Another surface here. And I'm interested in this, I don't even know how to describe it, shape that's in between. those surfaces, right? That yellow sort of, I don't even know what to call that. But anyway, that yellow surface. And you can do it the brute force old-fashioned way if you want. You can slice the slices, etc. But let me just try to show you what you're going to artistically be up against if you do. Drawing, for example, a Z-slice. Okay, challenge time. I hope I can do a reasonably good job of this. Something like that, isn't it? Well, that's terrible, right? That's a hard thing to draw. I don't want to have to try to do better than this. Very confusing, undesirable to try to draw slices. Notice, though, there's a great projection opportunity, right? There's a wonderful projection over here, again, in the direction of the XZ plane. Your lower surface, always that one. It's not that bad. It's perfectly consistent. Fine. Your upper surface, always that one. Consistent, always the same equation, not that bad of an equation. We have here a really good projection to the XZ plane, so we put XZ on the inside. Outside. Put XZ on the outside. Yeah. Side note. That's the same I would have gotten if I'd motivated it the other way. I really like that y is a function of the other variables, right? And I don't want to have to solve for x. I don't want to have to solve for z. So if I take that sort of like, put the dependent variable on the inside point of view, then that gives us the same motivation, sort of from the opposite point of view. We want dy on the inside for algebra reasons. We want dx dz on the outside for geometric reasons. And now you slice up your projection. It's just a disk. Green to blue. Solve for y. Oh goody, it's already solved for. And so your bounds, right? You get these bounds for x and z from the projection. And then from green to blue for y. And we're in business. What do you think? Everybody okay? All right, we're out of time. So calling it a week. Y'all have a good weekend. See you on Monday. And, have fun. Okay. Oh, as usual, stick around if I